Thank you, Andy. Thanks so much for having me here. It's a wonderful time that I'm having here discussing, and I already learned a lot of things, especially about this topic, quantum transport. That's one of the foci of the research in this institute. So it's really wonderful to learn, what techniques are available to tackle this problem. So what you will see later in the talk is fleshed on here already just as an appetizer. These are sound waves. So the gong was actually nice, the kind of introduced sound into this story. This is what happens when we gong, so to speak, our unitary Fermi gas, strongly interacting Fermi gas. And it's literally a gong because it's audible in principle. Well, okay, it's a vacuum chamber around it. It makes things difficult. But I could, in principle, sing to my mirrors. The mirrors deflect the light onto our atoms, and they would then vibrate and would be resonant with the sound modes in our box. It's pretty hilarious. It's like a few hundred hertz, just for the sense of scale. Spatial scale is 100 microns, roughly. So that's a unitary soup. But let's go slowly. Of course, here I don't have to introduce the importance of understanding strongly interacting Fermi systems. So the course that I took with Antoine in Paris was électrons fortement corrélés dans les solides. Okay, you can guess what that means. There's some electrons in there and solids, and fortement corrélés. So somehow that stayed with me throughout my career, and I'm still working on it. Antoine, you somehow are responsible. You launched this thing. What can I do? It's beautiful because it explains. Well, it correlates with many things that surround us, from the nuclei to the neutron stars that we are now seeing in LIGO. And as you know better than anyone, these are hard problems to tackle and to understand, especially when it comes to dynamics. For example, can we understand nuclear fission as a dynamical process? People are making strides towards that. You all are very familiar with the complications in high TC materials, for example, but also all kinds of other strongly correlated systems. And well, since LIGO had this wonderful result, now we can show these beautiful pictures, which are, of course, artists' renditions of what is actually going on, of neutron star mergers. And you might wonder, hey, maybe so when you really zoom into what's going on in a neutron star merger, you probably need to know the equation of state of these neutron stars, and you need to know about sound and dissipation, possibly, that happens when these guys come together. So transport, well, it's about the most difficult property to understand. I learned this from you guys, not the other way around. So especially, apparently, DC connectivities are the worst that I can ask you to calculate. And the word DC is a terrible pain. It starts terrible pain in your heads, because that means I need long evolution times. That's a problem. We have strong interactions, so usually I don't have quasar particles at play that I can use for some, say, Boltzmann description of the motion. And well, in some approaches, there's the fermion sign that comes about. And I call it conventional Monte Carlo because when I gave this talk in front of Boris Svistanov and Nikola Prokofiev, they said, like, wait a second, it's, our Monte Carlo is profiting from a sign blessing, not a sign problem. So I was like, yeah, it's just true. But so usually it poses a problem that these fermions are intercorrelated, and you have to make sure that whenever you find two fermions in your wave function and you exchange them, there's a minus sign. So that's why it's actually now very interesting to study these pristine models of like fermions, say in 2D, in a lattice, ideally in a box potential, so we don't have to worry about some trap, and just watch them go and measure transport coefficients directly, get hard numbers out with error bars, and then compare to various theoretical approaches. So I think it's very nice that now both the experimental situation is improving more and more, and also the experimental tools are being developed, actually many of them here, to tackle quantum transport. So it's an exciting time actually to come and talk to you about what we have done. I thought it's first nice to think about impurities, because before understanding the whole complicated soup of many interacting particles, it's maybe nice to take a single impurity and move it through a simple background. For example, move it through a Fermi gas, a non-interacting Fermi gas. but let the impurity be very strongly interacting with the fermions. Or take a Bose-Einstein condensate as your host material and put an impurity through that. So already there we can start to see the big issue that you get once you try to understand transport. Let me do this here with the example of an impurity. There's going to be a Fermi gas, the background. So these red particles, think of them as fermions. My blue guy is an impurity particle. At high temperatures, when I have when I have unitarity limited interactions as strong as quantum mechanics allows, my scattering cross-section is just given by the de Broglie wavelength squared. So that's actually a very nice universal place to study these systems. My scattering rate, if I plug it in, is therefore, after a few lines, going to go like 1 over the square root of temperature. The prefactor is already universal. It's the Fermi energy divided by h bar. That would be the classical Boltzmann regime, however, of unitarity limited interactions, so particles that interact at unitarity. The lifetime of these quarter particles could become very, very long at high temperatures. Yes, we simply have bare particles scattering. The energy uncertainty of these guys, which you could say is roughly given by the inverse lifetime, is therefore much, much smaller than the typical energy, which is kT itself. So well-defined, not quasi-particles, but real particles at high temperatures. But let's go to low temperatures. And at low temperatures, of course, in a Fermi gas, I expect that I have Pauli blocking of collisions. I have a scattering rate that now goes down like t squared. That's the usual phase space argument, right? I have a number t of guys that can actually scatter with me, and they have final states proportional to t that they can scatter into, so I get t squared. Now again, I have an energy uncertainty, h bar gamma, which can also be much, much smaller than the typical energy scale of these particles, which is on the order of the Fermi energy, the only energy scale available in the system at low temperatures. And in fact, that means also you get beautiful quasi-particles at very low temperatures. The Fermi polaron emerges. So that's a dressed quasi-particle which has a dressed energy minus 0.6 times the Fermi energy. But what happens in between? We can study this question with a type of spectroscopy. It's radio frequency spectroscopy. What it does is think about your spin up and spin down atoms. In this case, I have actually just a single spin down in a sea of spin ups. And imagine I can flip one of these, for example, the spin down, into a third spin state, number 3 or spin right if you want, that is not interacting with the original spin down or spin up world. That way I can really probe the energetics of this particle. I can ask how much energy does it cost me to bring this guy into this final state that measures the polaron energy. And also, as I try to do this, I'm attempting to do a coherent drive, right? I'm trying to spin flip this atom from spin down into this final state. But if there's a fermion out of the Fermi sea coming along and scatters with me, I will interrupt the coherent evolution. And so this will give me a broadening of my spectral lines. So now that's how you can now interpret these spectra. At low temperatures, you see a rather sharp spectrum centered at the shifted 0.6 E Fermi energy. But at larger temperatures, you see how the spectra broaden. And that immediately tells you, okay, so the lifetime of these polaronic quasi-particles decreases. And in fact, it decreases so much that the width here is on the order, again, of the Fermi energy itself. So you are in this regime where you don't have well-defined quasi-particles anymore.
Martin, can I ask a question here?
Yeah.
Am I correct that this being RF spectroscopy and hence integrated over the final momentum, the width of this distribution is anyhow not directly the scattering rate? Isn't there a K integration?
Yeah, that's totally right. That's totally right. So that actually can contribute to the width a little bit. But okay, if you make a simple assumption that you have maybe some Lorentzian spectral function you integrate over it, it's not doing such a terrible thing to the width. So actually the width
at high T, I think I would agree, but at low T, I'm not totally convinced. But we can discuss that at some other point.
Yeah. Well, at low T, actually, you see it shrinks to pretty much a delta function. So it's actually all good at low T also. this is the width now as a function of full width half maximum. And actually what I did here so at low temperatures you see something that looks pretty much like a quadratic increase in the width. So again, at low T, if the width is small, the integration that Antoine was talking about over all the final momentum states is not important. It could start to contribute around here to give you an additional width. At high temperatures, I can do sort of a high temperature calculation that asks what is the typical spectrum of such a high temperature impurity that I throw into a gas. And there I can do the integration, and it's true. It's not a simple, it's not a simple Lorentzian anymore. The shape is a little bit different. I wanted to spare you that detail, but you do get a width out which is agreeing with the experiment. So this dashed line, there is no fitting parameter here. This is just coming out of a high temperature calculation. This line is also predicted without adjustable parameters, and I have no idea why in the intermediate regime there is still sort of a good agreement between the left and the right side. There's no reason that has to be the case. But you see the point is the full width half maximum, which tells you about the decay rate of these quasiparticles, becomes on the order of the Fermi energy in this regime. And so you don't have a good quasiparticle description. It was pointed out by Sachdev and oh, you had a question.
Yeah, just experimentalist question. Why are the error bars so asymmetric and on different sides, like the vertical?
You mean x versus y and even the y?
The y, yeah, are very asymmetric.
Yes, so because the spectra, so it's not quite, like here you would say, oh, the spectra look very symmetric, right? But I didn't show, well, they don't look super symmetric. And at higher temperatures, they look even less symmetric. So actually, you have you're trying to take into account the fact that these spectra are not symmetric. So you want to actually do justice to that, and so your error bar should actually take that into account. It's a little bit a stupid detail, but it has to do with the line shape not being a Lorentzian. Right? Yeah.
So what is the negative?
There's Claudio! I'm like totally shocked. Claudio's done. Without him, we would not have this data because he built the oven. Now that is crazy, right? You didn't expect that to happen. I didn't expect Claudio to be here.
So what is the negative frequency?
There's Sebastian! Okay, that's fantastic. Sebastian is also here. Great. So, 10 years. This is great. Yeah, I haven't seen him in like 10 years roughly. Claudio, yeah, sorry.
So what is the negative frequency?
What is the negative frequency? You mean here?
Yeah.
Yeah. Oh, yeah. So 0 here means that's the atomic transition where you that's how you would use R spectroscopy for atomic clocks, for example. So dilute gas, you get a nice delta response at 0. So we take out the Bright-Raben formula and the Zeeman shift and all that stuff. But of course, we can tune around that and just see what happens. And actually, if you have a finite momentum quasiparticle, you can actually transfer it to the final state at a little bit of a negative frequency, because it can, at the final state, have 0 momentum, and the momentum difference can be taken up by the bath. Yeah. So it's funny. You can actually, in principle, you can totally get transfer at negative frequency. Yeah. So typically, for a hot temperature spectrum, this goes down to roughly minus T. Minus the temperature is the onset of the spectrum. Yeah. Good question. Other questions? Oh, well, it's good. I wanted to just point out that there's this connection to this quantum critical world that are usually discussed in you would say at 0 temperature there are quantum critical points of certain, for example, Bose-Hubbard models. But actually, Sachdev pointed out, hey, actually you can understand this strongly interacting Fermi gas at Feshbach resonances also by being in the vicinity of a quantum critical point. Yes, also at 0 temperature, but also going into the limit of 0 chemical potential. Now we don't live at 0 density. We live at finite density. So there, the point where chemical potential is 0 is always at some finite temperature, on the order of like 0.7 or something like that. That's where we are closest to this quantum critical point. We are not at a point. We'll never encounter a point here. We will always be in a quantum critical regime on top of the point. But it was pointed out that's actually a nice way of connecting this low temperature to the high temperature behavior. And it's the usual story that you hear in other contexts, that near a quantum critical point there are no quasar particles. So there's actually a connection. This is a little bit going away from fermions, but I just love it so much that I had to actually talk to you about the Bose case as well. It's very recent, so I threw these slides in. It's maybe not a fully coherent presentation, but I just wanted to throw it in here. I now throw an impurity into a Bose-Einstein condensate. So very different host bath. And at high temperatures, though, I would expect the same as before. I have a thermal Bose gas. I don't care that there are bosons actually at high temperatures. So same as before. At low temperatures, I should find a Bose polaron, which is, of course, a paradigmatic quasar particle in condensed matter. And so it's quite interesting. You could ask, actually, this should get a question mark. What's the decay rate for these Bose polarons? And in a certain regime where phonons play the dominant role as the excitations that this impurity creates, you should expect something like a T⁴ decay rate, just because that's how many phonons there are at a finite temperature in terms of what's the energy density. Let's see, what would we find? And now that this crowd of people did this heroic experiment where they took actually a Bose-Einstein condensate of sodium and threw in some potassium fermions. This is actually the experiment that Sebastian used to make sodium-potassium molecules. Sebastian Wille, by the way, in the audience, who people don't know him. Oh, probably people know him here. But now here we don't make molecules, we just make impurity atoms, fermions, and these are grad students on the project, Zoe, Yichi, and Alex. Elisa was a visiting student, and Carsten Robens is the postdoc on that experiment. They took these impurities and looked at what happens when I confine my fermions into the Bose condensate. And so this is the situation. You have a Bose condensate, you have some Fermi gas that you overlap, and now you see what happens as you try to transfer these fermions into a non-interacting spin state. So same as before for the fermions. And now you see, wow, I have to detune quite a bit in terms of, well, kilohertz doesn't tell you much, but let's say 20 kilohertz is a typical Fermi energy, an energy scale given by the density of the bosons and H bar and M. So these are quite strongly shifted spectra, and that's what you can also see if you spatially resolve the spectra here. Where the condensate is, there's a huge shift and actually a long tail to high frequencies. So you can now take your local density approximation hat and just consider each region here as a local box of homogeneous background density and analyze these spectra normalized by the Fermi energy. So this is on the right side here you find the normalized spectra. Here you have unnormalized spectra. And you see strongly shifted spectra. And if you squint your eyes, you also see that the peak shift is first positive. So it looks as if the Bose polarons become more strongly bound at finite temperature. I will give you that there's a caveat about precisely Antoine's point that these are momentum integrated, and there can also be a shift due to the increasing width of the underlying spectra. So we don't know what this directly signifies, but this is what we see. But what is very clear is that you get this crazy broadening near the critical temperature of Bose-Einstein condensation, and then it shrinks again at high temperatures. So just to summarize that, those findings, we find very strong energy shifts in this near-resonant Bose polaron case. So again, a polaron energy, which is on the order of the Fermi energy, and then I should stop using the word Bose polaron, I guess, because it's very strongly bound and it has a large width. But at low temperatures, it seems to have a very nice, very well-defined, very small width with a small scattering rate. And you see, I cannot help but call it a linear in T, scattering rate. It looks linear to me. Of course, it's not a full decade of data, but it looks pretty linear to me. We have no idea why it should be linear, by the way, but it's just intriguing that also in this strongly interacting regime of impurity in a Bose-Einstein condensate, you seem to see a scattering rate that grows linearly with temperature.
Wait, I'm sorry, do you ever see the predicted T⁴?
No, we don't. In fact, we don't even see it in the energy. In the energy, it should also be T⁴. Here's the very simple argument. I have here energy scales on the order of the Fermi energy, much, much, much larger than the chemical potential of the condensate. The chemical potential tells me the energy scale up to which I will expect phonons as the quasi-particles. Whereas here, I have like many times, 30 times that energy scale that I find. So most of my dressing of this impurity comes, it seems, from from actual particles, bosons being kicked out of the condensate by the impurity and not by phonons. That I think explains why we should not expect the T to the fourth behavior. There is probably a scale at which you would see it, but it's way at super low temperatures that we don't reach on the order of, well, T to the fourth is anyways hard to see. So that was a little bit, I know it was a bit quick, it was not the full thing. I was just trying to tell you impurities might be a good way to start understanding transport because, you know, they already give you, is there reality to the concept of a quasi-particle or not? And now we will actually study bulk systems where we throw in as many blues as reds or as many ups as downs and study transport in a strongly interacting unitary Fermi gas. And we'll also switch on lattices in another experiment, actually, to study fermions in optical lattices and study the transport in the Fermi-Hubbard model. So the first part of the talk is done by this group of wonderful people, Parth Patel, Zenji Yan, Biswarup Mukherjee are the graduate students on the project, and Julian Struck and Richard Fletcher were our postdocs. Julian went to the École Normale, and Richard is the current postdoc on the experiment. So the tool to use is Feshbach resonances. That simply means you take two fermions, or two atoms, doesn't have to be Werners, and you bring their energy into resonance with the energy of a molecular bound state. And when that happens at a particular magnetic field, you have strong scattering. So it's very simple in the lab. You just have to apply the correct field, and then you can explore very interesting states of matter that are born out of these strong interactions. For example, on the molecular side of things, we can make a Bose-Einstein condensate of molecules, tightly bound fermion pairs. Of course, that should be a Bose-Einstein condensate. We can also go to the attractive side of the Feshbach resonance, where the pairing is a purely many-body affair, which connects to the Bardeen-Cooper-Schrieffer superfluid. And in the middle, we have a crossover superfluid, where the pair size is on the order of the interparticle spacing. So a long time ago, we demonstrated that these guys are actually superfluid by spinning the gas up, taking our PowerPoint spoons, rotating it a couple of times, and seeing a vortex lattice appear. So okay, great. We know at low temperatures this unitary Fermi gas is a superfluid in this entire regime of molecules to BCS. But let's focus now on this unitary gas where the interactions are as strong as quantum mechanics allows. There, it's a beautiful point because the equation of state at this point can only depend on the density of the particles and the temperature. So in terms of length scales, the interparticle spacing, the de Broglie wavelength are the two only distance scales that play a role, or there are only two energy scales correspondingly, the Fermi energy and the temperature. And especially interesting point, or especially nice point from an equation of state point of view is at zero temperature, the energy of this complicated gas can only be some number times the energy of a non-interacting gas. So even though it's very strongly interacting, it is simple in some respects in terms of some things that you already know just by knowing there are no other scales available here. And this prefactor is actually hard to calculate again, but the experiment gives 37%, and actually that's also born out of theoretical calculations now. To prove to you that these guys are strongly interacting, the best thing I can do is I can take a spin-up cloud and throw it into a spin-down cloud and see what happens. And these two clouds, even though they're a million times thinner than air, they actually bounce off each other. Yeah? That's very strongly interacting soup. Again, the scale here is 100 microns, and they bounce off each other. So that already tells you, wow, they're very strongly interacting. In fact, the mean free path is on the order of the interparticle spacing, as short as it can possibly be for contact interactions. The average velocity in such a Fermi gas in the degenerate regime will also be given by the interparticle spacing, just by de Broglie, basically. The velocity is going to be h bar over m times the interparticle spacing. That tells me that whenever I come up with some diffusivity of something, of maybe charge, spin, momentum, or thermal diffusivity, heat transport, I will end up with a number, d, diffusivity, which is the velocity times the mean free path, which is going to be sort of universal. It's going to have the units of h bar over m, and maybe a prefactor that depends in interesting, complicated ways on temperature, but basically h bar over m will set the scale. So that's what we will find throughout. This is a not nice to read attempt at summarizing transport properties of Fermi gases extracted from experiments in the past. What was often difficult, I mean, there were wonderful experiments on for example, second sound, charge transport, collective oscillations. They were usually happening in a harmonic trap. And you have lots of issues with these harmonic traps. Sometimes it's nice, because they give you a scan through the phase diagram. But for transport, it's really not so nice, because you have inhomogeneous densities. That means you will probably inhomogeneous transport coefficients that you sort of average. And you might even end up doing transport in different states of matter. So it's very complicated to disentangle. Hydrodynamics, you would expect for a strongly reacting gas, but well, not at the edge of your harmonic trap, so that's a problem. And the spectrum of collective excitations, it's actually quite involved to understand. It's a bit difficult to access, and actually the lowest mode is boring. The lowest mode of a collective oscillation in a harmonic trap is just the sloshing mode, left and right, which is going to happen at the trapping frequency. So the lowest mode is already not interesting. Let's go to a situation where the lowest mode is interesting, namely a box. Yeah. So you need this guy, Zoran. Claudia knows him very well. He spent many, many nights with Zoran in the lab. He introduced the box to a Bose gas and brought it over to MIT, basically. This is a box at MIT on fermions, and there are more boxes around the world, I guess more than fit on this slide. But this is wonderful for transport, for studying critical phenomena, correlations, novel phases, etc. So I hope to convince you through this talk that boxes are awesome. When you are a physicist, you have some new soup in your container. What you do is you wiggle the container, and you create, well, sound waves, right? So let's try this. It doesn't look like much, but actually let me subtract the background from this wiggled image, and you do see, yes, there are sound waves propagating in this soup, just like in the textbook. Okay, now we can do first things first, figure out that the dispersion is what you expect for sound, namely linear, frequency versus momentum, and it's really quite nice. You can just wiggle at the particular frequency, you get a particular spatial pattern that you can just Fourier transform, you get your K. It's a very direct measurement. And what about the speed of sound here? And there's many digits of precision, but of course we have to compare it to something. In fact, I will tell you right now that Einstein was actually wrong. So it is dramatic, I know. The energy is 9/10 of mc squared, if you didn't know. He was wrong, You're very confused, but we are actually printing these t-shirts now. 9/10 mc squared. What is going on? I'm calculating the speed of sound, not of light, by saying mc squared is the derivative of pressure with density at constant entropy. But my pressure, by scaling, I'm at the unitary point, it can only be some universal function of the entropy density times the pressure of a non-interacting Fermi gas. But I keep entropy fixed, so that comes out of the derivative. And I know how a non-interacting Fermi gas pressure depends on density, so I get the 5/3 in front. Oh, great. And then I also know that pressure equals 2/3 times the energy density for the scale invariant Fermi gas, just like it is for a non-interacting Fermi gas. And I get mc squared is 10⁹ E over n. And you can make a plot where the x's are energy per particle, mc squared on the right side. Here it goes from 0 to 9, here it goes from 0 to 10. And yes, it's on that diagonal on this plot. So this is actually correct. What's funny is that you don't see here which points were taken in the superfluid regime and which points were taken in the normal regime. It turns out, our fluid is very hydrodynamic, far above Tc even. So it turns out only the lowest 4 points were taken in the superfluid regime, but they all lie on this curve. Let's understand a little bit more what's going on by doing the next thing that the physicist does. For example, a physicist in a bathroom feels the urge to sing. and figure out what are the eigenmodes of the bathroom. And so you sing, and then you get discrete states. And it's quite beautiful to do that because as you sing, and these are frequencies that you could sing totally, 400 hertz, 600 hertz, you will see standing waves. Let's wait until the movie replays because the lower order modes are a little bit clearer than the higher order modes. Here it goes, 0. Some stuff is happening. Let's go to this first symmetric one. That looks nice, right? Let's sing a little bit higher frequency. Second symmetric one, right? And so on. Yeah. So that works well. And now gives you a lot of information about, well, sound and sound dissipation. So that's where the transport comes in now, because how does sound actually decay in our fluid? We can take these data, integrate them over the boring direction, and plot them versus frequency. So then we get this sonogram, basically, of our unitary Fermi gas. You see very sharp resonances at low frequencies. This is, for example, the sloshing mode, where they just slosh back and forth. This is the first symmetric mode, the second symmetric mode, the second antisymmetric mode, and so on. But by eye, you already see they become less and less well-defined in frequency. Yeah? The whole thing broadens and smears out. We can bring this out more clearly by taking the spatial Fourier transform. Now we have k on the y-axis versus frequency. We see, oh, it's a linearly dispersing mode, but you also see it becomes washed out at higher momenta, or higher momenta/frequencies. If you have good eyes, you can see even a second branch. This is actually second harmonic generation of sound in this fluid. Pretty cool to talk about a fluid when you started with a gas of lithium-6 particles, but it's what it is. We have hydrodynamics. So let's actually try to use hydrodynamic equations to understand what's going on. We have certainly the continuity equation. Mass doesn't go anywhere. We have the Euler, or I should say Navier-Stokes equation. The moment I put an eta in there, it becomes Navier-Stokes. That tells us about momentum transport that is damped through viscosity. One good news is for this unitary Fermi gas, it costs absolutely no entropy to just scale all dimensions by this common factor. So since that doesn't generate entropy, there is no so-called bulk viscosity. So there's nothing that costs me when I dilute my gas in all directions equally. So I only have shear viscosity. So if I pull a plate through, I will actually see the relaxation of that perturbation over some spatial distance, which is given by the shear viscosity. That is still there. We also have heat transport. We have thermal conduction, and that is, of course, governed by the thermal conductivity of the gas. So we have only two transport parameters here, which is nice. The viscosity eta and the thermal conductivity kappa. They conspire, both of them, to cause the damping of sound. Viscosity, that's maybe you might be used to. Viscosity damps you. But also thermal conductivity damps the sound wave because sound does couple to temperature. And when it couples to temperature, then you can actually dissipate this temperature gradient by heat, and that's how the sound wave can lose energy. So it's a little bit, it looks like a complicated formula, but it's actually much easier than for, say helium or something like that, because we know derivatives of, say, temperature with pressure or temperature with density at constant entropy. They're all simple and give me just things like T over P, for example, here. So it's a kind of nice equation. The dispersion relation, therefore, it has this omega equals ck in it, but now I also get damping, where the damping is quadratic with momentum. To remember that, recall that viscous forces, they're proportional to the gradient of the velocity field, right? But if I'm a slab of air and I'm getting pushed from both sides by the same viscous force due to the same gradient on either side, I will not feel any net force. So I need a curvature of the velocity field in order to push me around and damp me, and that's why you have the k squared there. Okay, so let's now plot the Fourier transforms of what you have seen here for all these various modes as a function of frequency. And you see again, we get sharp resonances at low frequencies and broader at high frequencies. Actually, for you, I can say this is a direct measurement of the density response function of this gas. It's kind of nice. It gives you a direct spectrum of what's going on. But now let's plot the width as a function of frequency and see whether it's quadratic in nature. And yeah, it's sort of quadratic. It works well. It's some lab units, right? You have like hundreds per second damping rate versus some hundreds of hertz, which would turn into thousands per second of some angular frequency. But it turns out if you now take the ratio of gamma over k squared, you get a number that is very close to h bar over m. Yeah? Without me putting an h bar over m anywhere, it comes out to set the scale, and it becomes 2.1 h bar over m. So this seems to be telling us that there's some quantum limit of sound diffusion going on here. And at this point, I had to stop and think about what is known about sound diffusion or viscosity in other superfluid systems or other interesting quantum liquids. There are not so many around, so let's look at helium. And let's look at helium-4 first. Helium-4 has this intriguing behavior of the viscosity as a function of temperature. Nothing super terrible dramatic happens at Tc. Tc is this little point here at 2.2, I think, Kelvin. Yes, the viscosity does go down, but only by a factor of 2. You might have grown up learning the viscosity of superfluids is 0. Well, that's not true. What is missing with that in that sentence is that you have to say through narrow capillaries. Through narrow capillaries, because they will clamp the normal fluid so that it cannot go, and only the superfluid can go without viscosity. But if you are in the bulk and you try to push some sound wave through, there is always normal fluid, and you will always have viscosity even if you're already below the superfluid critical temperature. And that's what they find. And now you ask, 10 to the minus 8 meters squared per second, that's really an awkward thing to remember. Turns out it's h bar over m. Yeah? H bar over the mass of the neutrons. And then eventually it actually goes up again. That's due to phonon scattering. I don't want to bore you with that, but it's actually interesting. At low temperatures, phonons take over and make it very sticky. We have a Fermi gas, so I should probably compare to helium-3 rather, right? Helium-3 has this totally different behavior of the viscosity. I lower my temperature and I get up with viscosity. It becomes very sticky, like 1 over T squared. What is going on? Well, first of all, h bar over m is down here. So actually, right when it becomes liquid, that's when it actually already has a quantum scale of viscosity in it. But then, actually, helium-3 is the best, maybe the world's Fermi liquid. Not even the best, it's the Fermi liquid. It goes like 1 over T squared. That immediately tells you that the scattering rate is now getting Pauli blocked, and you get a very, very sticky substance here. You might ask, okay, but then it becomes superfluid at some point. Yes, at a few millikelvin it becomes superfluid. What happens to the viscosity? This is the place, 1, normalized by the viscosity of the superfluid. It's actually very sticky still. Then it does drop by a factor of 10. It's pretty remarkable, but then it actually stays roughly flat. It doesn't go to 0. And at that level here, it's 1,000 times h bar over m. So it's actually very sticky. Well, very, like it's quite, it's nothing remarkable in terms of its viscosity. I can give you a hand-wavy argument why there is a constant viscosity in helium-3 at low temperatures. Viscosity is always about how much normal fluid do you have sitting around, and what is the lifetime of the quasiparticles that are doing the scattering. So the normal fluid density, you would say, that decreases to 0. So your intuition says I should have 0 viscosity at 0 temperature. That's not correct, because the quasiparticle lifetime also increases exponentially with lowering temperature. So these two factors actually cancel, and what is left is a viscosity that looks as if you had a thermal gas, the thermal Fermi gas, at a temperature T over Tf that's on the order of the pairing gap over Ef. So it's, the pairing gap takes over the smearing of the Fermi surface due to temperature, and the equation for viscosity stays the same. But Ef over delta is very, very large for helium-3, and for us it's on the order of unity. So let's see what we see. This is what we see. This is the diffusivity, sound diffusivity versus temperature. Here we are entering the degenerate regime, and it keeps going down. The solid line is the classical prediction for a classical Boltzmann gas interacting with unitarity limited interactions. The green line is calculation by Willem Zwerger, Hausmann, and Tilman Enz to of the viscosity. And to make a plot of sound diffusivity, I had to assume something about the thermal conductivity. I just assumed that they're related, just like at high temperatures, with a universal number, which is called the Prandtl number. And I used Prandtl 2/3 as it is at high temperatures to generate this green curve here. It's pretty ridiculous. It looks very, very good, actually. It seems like our measured Prandtl number is a little bit lower than 2/3. Lower means thermal conductivity has more of a role in damping the sound wave than you would think. What happens when you enter the superfluid? The superfluid occurs around 0.17 T Fermi, 17% of the Fermi temperature. It's actually the strongest Fermi superfluid, if you want, when you scale it by the Fermi temperature. You see the condensate fraction shoots up there, but nothing spectacular happens to the diffusivity. Yeah, it goes down a little bit, but it's basically flat, as we expect for for superfluid Fermi gas. So I would want to ask, what is so dramatic about becoming superfluid then? If the sound is not showing much. Well, there is this thing called second sound. So let's do actually two fluid hydrodynamics now. We have the continuity equation still. We now say that there is damping only from a normal component. Let's say it has velocity Vn, still with the shear viscosity in front. And we still have the entropy equation with thermal conductivity, but the entropy is only transporting the normal fluid. That's why you have the normal fluid velocity here. And you have a fourth equation, which is superfluid flow. Yeah? And actually that is totally undamped if you don't have superfluid turbulence, if you don't have a vortex tangle that the normal fluid could interact with. So that's why it's called super. Yeah? That's why superfluid flow around the ring is not damped, yeah? Even at finer temperature. So what do these equations give us? Well, they give us two sound speeds, not just one. They give us first sound, which is pretty much it's just a density wave, and they give us second sound, which to first or zeroth order you can call an entropy or temperature wave. And the entropy and temperature wave, they know about the superfluid density, because above TC, thermal, if you make a thermal hotspot, that will just diffuse, it will not propagate. But below TC, it will not diffuse, it will beautifully propagate. So that's the essence of having a superfluid. Superfluid, second sound in superfluid Fermi gases was seen in Quasar 1D trapped samples beautifully in the group of Rudy Grimm, where they actually heated the gas radially and watched, indeed, a second sound wave propagate out. How did they watch it? Well, they looked at the density, and thanks to a coupling between temperature and density that you normally have in gases, you could see this temperature wave directly in the density. Let's do this, a similar experiment in our gas, but in our boxed systems now. And let's actually do the simplest thing ever. Just take a gradient that I apply, and I just oscillate that gradient on top of my box. Yes, that will create lots of first sound, I'm sure. Yeah? But it should also couple a little bit to second sound, because density and temperature are coupled in our gas. So let's see what happens when we do that. Well, you get a big peak at here 80 Hertz for the first sound mode. This is the sloshing mode that you excite. It's a beautiful peak. And actually, to see this possible resonance, we have to increase the strength of our drive by almost a factor of 10 to tease it out here. There is maybe something that you could call second sound, but I'll admit it's not great. So what we should use is a local thermometer. Oh, just easy. I just stick in some local, well, we cannot stick in a local thermometer. So how do we do it? We actually have, and we're quite happy about this, a local thermometer for heat transport. And it's again doing what we did before for the spectroscopy. We have our 1,3, that's my spin up and spin down, or red and blue world of paired fermions. And I take an RF photon and bring them into some empty state, one of them into some empty state. And the spectra look like this. Yeah? There's a whole talk I could give about those spectra, but at the moment all we need is they depend on temperature. Great, because that means I can now sit at a particular frequency, somewhere in between, maybe like here, at this point. somehow on the left flank of this low temperature peak. And if the gas cools, I will see less transfer. If the gas heats up, I will see more transfer. So I will have to first order some linear response of temperature, of my transfer fraction with temperature. So it's an atomic physicist dream. You know, we have an RF spectroscopy for measuring the local temperature. Bam! If you do that, we see the second sound peak totally come out of the noise and become a beautiful, beautiful peak, and we have basically lost our first sound peak. So that shows the nice complementarity of first sound and second sound. One we see mostly in the density, the other we see in the heat. And what I didn't tell you is that those two pictures came out of the very same sequence of runs of the experiment. Because whenever we take an RF spectrum, we can of course also look at the total density. And so these are recorded simultaneously. So that's kind of a nice story. Great. Preliminary data. It's unfortunately, the machine has some terrible troubles at the moment. Shows the second sound speed down here quite low, and the first sound speed quite up. And this is getting there. I mean, we're filling up that curve. And we can also extract in a preliminary way the superfluid density directly. And well, it does what you expect. It grows from TC to something. But it's nice because it's very difficult to measure in other ways. And just measuring second sound is a very nice way. I should say the Innsbruck group used their data in this Quasar 1D version, tried to extract the 3D situation, also assuming our equation of state, and got the superfluid density. It does seem like we don't quite agree with them, but like it's too early to put the two together, I find.
Excuse me, was this 2D or 3D?
This is 3D.
Okay.
This is 3D. Just as an outlook for this story, we now can also measure the damping of second sound. This would be the width of these resonances that we see. Or more easily, we can just make a second sound standing wave and just watch it decay. You know, and it's quite nice. You can just measure that decay. And now we have two peaks, first, second sound, and two width. And we only have two unknowns, shear viscosity, thermal conductivity. So in the future, we will be able to extract both individually, which is nice. And then, of course, hopefully we learn something. Good. How much time?
What time is it?
To have?
50.
So 10, 15 minutes?
Oh, great! Yeah, that would be on a need, because I wanted to talk to you about the lattice world in the last 5-10 minutes or 5. Let's see how it goes. This is done by this group of students. Matt Nichols is a lead student. He's graduating actually next week. Yes, Matt and Thomas is the new graduate student on that experiment. And two postdocs. Hao Zhang is going to leave us to someplace. I think it's a secret. And we have Gia who came over from John Simon's group in Chicago to work with us. So this is on realizing the Fermi-Hubbard model. And I don't have to tell this audience that it's awesome to do. It's complicated to do. I actually learned a beautiful piece today about some stuff about the Hubbard model that I totally was oblivious to. So you know everything about the importance of that model and how difficult it is to treat, and especially to make a connection between this simple model and the real phase diagram that is seen in the cuprates, which by the way is also asymmetric in terms of particle and hole doping, so it's complicated. We hope to use these atomic systems to shine light onto, well, the Fermi-Hubbard model. Not the cuprates, way more complicated than what we have. So there are now Mott insulators under such microscopes realized in a variety of labs. I should totally update that reference. Of course, this builds up on earlier work in Emmanuel Bloch's group. Actually, Sebastian was among the first to make a Fermi Mott insulator, and in Tilman Eschlinger's group also, and beautiful work on Bragg spectroscopy at Rice. These days, well, we have large systems of the order of 2,000 fermions that make a nice, pancake Mott insulator, where you have roughly single atom filling, a uniform filling. but what you will like especially is that we also now make boxes of these things. So we get rid of the trap, flatten it out, and make a box of these fermions. And well, there again, you see at half filling, you see a Mott insulator. And if you don't have as many fermions as you have lattice you have a metal. And also if you have more than one fermion per side, you have a metal. And these holes, many of them are actually doublons. I'll have to say more about this at the end probably. Now let's apply a gradient to these things. Well, no surprise, if I apply gradient to a Mott insulator, nothing happens because it's an insulator. So, okay, this is proving the fact that it's an insulator, yay. If I do it on a metal, yep, they all go to one side as expected. It's not an insulator, great, it's a metal. And the same thing happens for our doublons, which here show up as holes, and therefore also go to the left side here. So, cool, so that is a nice transport measurement if you want. But it doesn't reveal what's really going on because it doesn't reveal spin. So what does spin do? If I do a spin-resolved imaging, it'll be interesting because it turns out the two spin states we use, they have different magnetic moments. It's not like spin up and spin down. It's not that they have oppositely oriented magnetic moments. They have similarly oriented magnetic moments, but different strengths. So you would expect that the blues like to go on one side, the reds, which have the stronger magnetic moment, they go to the left. And that's precisely what you see. So you see the segregation between the reds and the blues. So the blues go to the right, even though, in terms of their magnetic moment, they would love to go to the left, but they cannot because of the strong repulsive interactions. That's kind of nice. The moment you see this, you're like, okay, great, we can actually now do a transport measurement. We can either time resolve this splitting of spin up and spin down, or after having imprinted this gradient, just watch it relax. Those are the two experiments we can do. Let's do the first thing first. Let's take such an imprinted density gradient. Here's the density difference, and watch it relax over time. You see here 0, 17, 88 milliseconds. You just time resolve it, and you watch how it goes. This is the measured spin current as a function of the decay of the spin imbalance versus time, from which you can get the spin current for various interaction strengths. That we can dial in. We can also make sure we're in linear response by checking that the current is proportional to the density gradient that drives the current. So all is good, we're in linear response, and we can extract the, say again?
The density, what was the filling?
Oh, so we are at the Mott insulator, so we're at half filling. We thought that's a cool point to start with because when you do spin transport at that point, you're not messed up with some coupling of charge and heat or something. You just have the spin transport. Right? So it felt like it's a good point to do. I should say it's very difficult / at the moment I think impossible to do in cuprates spin transport. So we felt like that's a good thing to do. Temperature is on the order of tunneling. Yeah, T is on the order of little t.
Little t is small compared to U by a factor of 4 or something?
It varies. Yeah. So it's like 0.1, 0.2, the whole range. Actually, at very low T, you are, in your mind, you can say like you're now close to the Heisenberg limit, where you have frozen spins. But actually, as you see here, if I blow up this data is for the spin diffusivity that we extract from these relaxations of the current. The diffusivity does not agree with the Heisenberg result. Okay, the Heisenberg result should say that there's a particular slope. We are quite a bit higher. Well, we are not at 0 temperature, and so we might actually explore very much beyond Heisenberg stuff in our system. Also, we are not in the extreme limit. I mean, eventually it will go there.
Just to be sure, you're at a fixed temperature, which is of the order of little t.
It's not quite fixed temperature.
But a temperature, which is of the
I
order
can
of
show you.
T.
Yeah. Mm-hmm.
Then T upon U, which is J, is of the order of 0.1. So in magnetic language, your temperature is far above J.
Yeah.
And as you move to the left on this plot of T upon U, since your temperature is roughly fixed, the ratio of temperature to J is dropping as you move to the left in that direction.
Unfortunately, entropy is rather probably the thing that's better fixed. I'll show you in a second. But yeah.
But just if I think of where I am in parameter regimes,
yeah.
that in effect, you're comparing a fixed temperature or a fixed entropy and two different values of J if I compare T upon U of 0.05 and T upon U of 0.1.
Yeah, that's totally right. Exactly.
And I would have thought that, so how, this linear slope, is that just, I would have thought, this is just my ignorance, I would have thought that diffusion times, well, you've divided by 1 power of T, so the basically ultimate diffusion time should be J, which is T squared over U.
Perfect.
So this straight line is just T squared over U divided
Yeah.
by T. Is
Yeah,
that what?
exactly. I was not done explaining
sorry.
the subtleties,
Now I'm more
but
into
but maybe I didn't start explaining that slide in the right order. The units here. So the spin diffusivity is already normalized by sort of an atomic scale of diffusivity, which is, well, I have a certain rate to hop, that's T, and I have a lattice spacing A, so a unit of diffusivity is TA squared. Okay, fine. So I divide already by that to get some nice dimensionless number. Cool. And I plot it versus T over U. Okay, so now if we think we are in the Heisenberg world, everything should be governed by J, T squared over U. So I should see a linear dependence of this way of normalizing it versus T over U, and we do see that. Cool. What's not so cool is that we don't get the Heisenberg slope, but of course, well, we do not realize a Heisenberg magnet. We realize the Fermi-Hubbard model in this system at some high temperature, so it's more complicated. Yeah. In fact, we asked Ihsan Katami to cook up a time-dependent code to use the numerically linked cluster expansion to give us some time-dependent transport from which he can extract diffusivities and conductivities. There is a problem that the code, as you will sympathize with, dies at times on the order of the tunneling time. Well, actually, then it goes basically through the roof. And this line, there's no error bar because if I showed you what happens as a function of the cutoff time, it kind of sweeps out the whole range, right? It's difficult. That's what it is. But it's kind of nice, to show a plot where theory and experiments do not agree. That's good. That's where we start learning. Over here, we actually see a departure from this linear scale. It seems to go faster than linear. And that's a regime where we have actually lots of holes in the soup. I wish I had the images. I don't think so. Here it really looks like a happy Mott insulator if you take a picture. Over here there are lots of holes around that can be used efficiently for spin transport. You don't have to wait for super exchange. You can just tunnel. Right. So
Martin, can you say again what NLC is standing for in the inside?
Numerical linked cluster expansion. So that was used previously for thermodynamic properties. So I think it's a sort of coming from a high temperature expansion in some sense, where you expand in the cluster size that you take into account for your evolution in some self-consistent way. But here it's used for a time-dependent calculation of the current correlator, so that you then can take a Fourier transform to get the conductivity.
Well, there's always a question of commuting the omega equals 0 limit with the high T limit. So this is somewhat subtle to do from high T expansions, but okay, fine, thanks.
Yeah, I only understand it's hard. Yeah.
This is a very silly question. Your experimental curve is about 4 times the theory curve.
Yep.
So, did someone forget the factor of 4?
No. So, not in this plot. There used to be a version of this plot. No, I don't want it. This is public, right? So,
yes.
Okay, who cares? Ihsan, I love you. There was a factor of 4 in the theory that was off. And I hope you will never listen to this talk. But I mean, it's what happens in a scientific endeavor. You forget factors of 4. So we checked everything on our experimental side. What can we do to check that thing? We can use the Einstein relation. We can measure spin conductivity and measure the spin susceptibility, and also from that extract the spin diffusivity. So let's do that. See whether that works out. Oh, here I, by the way, have pictures. I'm happy that I have pictures. In this regime, it looks like a happy Mott insulator. Over here, I have more holes. So this is now a measurement of the spin conductivity. So directly, I apply the gradient, magnetic field gradient. I watch them drift apart, so I can extract the conductivity. And I can also use the Einstein relation to take my diffusivity and the measured spin susceptibility, which is here, to extract also spin conductivity. And the two agree well within our error bars. Yeah? You can say the error bars get large, fine, yeah, it's difficult. But we checked ourselves, right? So we feel fine. And we spend month and month and month for just checking every systematic and this state, our result state. So this is it. The spin susceptibility, by the way, tells you, okay, this plot doesn't quite tell you, but the temperature is not the one that's constant. It's more entropy that is constant in this world. Good. So now that's the end of my talk. I wanted to just leave you with unifying themes here of what's going on with these Fermi systems. You have a problem that you have a loss of your quasi-particle description. Your lifetimes of quasi-particles become limited by the only energy scale in the system near T over T Fermi on the order of 1 is kind of Fermi energy. But actually, to connect the first part to the second part of the talk, if you want to call the spin diffusivity we saw h bar over m, well, then you have to invent a spin mass, which is very different from the charge mass. So I don't know whether that's a useful concept, but what is good is that basically we get now these very nice measurements with error bars that one can compare to and hopefully provide insight. This is our wonderful group. Oh, I forgot that Zoran was there at the group. It's wonderful that he's there. He's usually in Cambridge. And I leave you with this slide, and thanks to the funding agency and you for your attention.
All right, thank you for this great talk. We had some questions during. Are there more questions?
Well, maybe I have one. So,
Yes.
if I remember correctly, there were some surprising results from Michael Kohl's group about spin diffusivity. I think also in 2D Hubbard, right? Am I correct?
I don't recall that.
Oh, it was not.
Is it published or? I don't remember. I don't recall.
I think so, but maybe I'm.
When was that?
A little while ago, and there were question of.
Oh, are you saying?
Very fast. Yeah.
I know what you mean now. There was a paper. There was spin transport and charge transport relaxing at different rates, right?
Correct. That's
something like that. Yeah.
My
yeah.
memory is a little bit.
I know that. I know that work. Yeah. I don't think they provided a number for spin diffusivities.
Okay, maybe not. Okay.
I don't think so.
We could just.
But sorry, I remember what paper you're talking about. Yeah.
Right. Other questions? Yeah.
So, can you ever get to the point where your sound becomes non-linear? I mean, you know that
Yeah.
every sound in a real material, at some point you get to compressibility, which is non-linear. So, is that experimentally realizable?
If I was super prepared, I would have a slide on nonlinear sound, and I think we might be lucky. Yes. No, not yet. Could I have one? Look at this. So this is one of these snapshots where we measure delta rho over rho versus, just in the box versus the spatial coordinate. You see a single sign doesn't do it. It's not a single sign. Oh, there's actually at least two modes here. Excited. So if I add the second harmonic, I get something that looks much better. Here's another example. Single sine wave doesn't quite do it. Oh, it looks better to use two. Well, that's one way of seeing that there's something going on. You can also zoom into these sonograms at some higher driving power, and you see, for example, the mode number 4. That's the second symmetric mode. It has a very nice resonance at its corresponding eigenfrequency, but already at half the frequency, you see it being excited as well. So there is second harmonic generation. So nonlinear effects are inherent in this thing. And here's another nice plot where we wiggle the second mode. It builds up beautifully, as it should. But the fourth mode also automatically gets gets amplified as well. So in that sense, yes.
So now I have another question. So do you think that this generation of second and fourth harmonic comes from the gas itself, or is it an artifact of the experiment? You know?
Beautiful. Well, we asked ourselves that question and checked, whether our drive is perfectly sinusoidal. And well, as much as we did, yes, it was perfectly sinusoidal, because what we wiggle is really just the intensity of one of the walls, right? So we just wiggle it sinusoidally up and down. It is absolutely no surprise to see second harmonic stuff. I don't know whether I have that here. Oh, yes. Every fluid, as you know better than anyone, if you decompose it into first the quadratic stuff, you get the sound, you get phonons, which is beautiful. But you can also go, so this is the quadratic term, you can also go to the cubic nonlinearities in your expansion of the sound energy, and you will get already, just by the fact that these are non-relativistic particles, they have actually kinetic energy density, rho v squared, which gives you a cubic term delta rho v squared. You already, from that, get second harmonic generation. In addition, you might have actually a third derivative of your density of states with respect to density, and that gives you another cubic nonlinearity. Turns out this one dominates the kinetic part here, which you always have, dominates over the part coming from the equation of state, in our case, by a factor of 10. So the nonlinearity we see, I'm pretty convinced, is just coming from the inertial term, coming from the kinetic energy.
All right, if there are no further questions, let's thank Martin again for a very stimulating talk.